Welcome to this module on astrophysics and cosmology. I'm sure that you will agree with me that there are few topics that interest humanity more than astrophysics and cosmology. And the reason for that is that we are all aware now in the modern world of how small our planet Earth is in comparison to the cosmos. The question is, why is the cosmos so big? Why are we so small in comparison to the cosmos, and yet we're the only place that we have found in this massive universe where we've found life? And as we've studied life scientifically, we've come to realize how complex it is and what a miracle life is. And through the efforts of physicists and astrophysicists and cosmologists, we have come to realize that the laws that govern the quantum world have in the past had impact on the cosmos. And so as we move forward in the 21st century toward what we hope we will eventually achieve, and that is a grand unified theory or a theory of everything, we look deeper and deeper into the quantum world and deeper into space. And the deeper we go, we find more. We find more on the quantum level. Think of the field of superstring theory, supersymmetry. We think of the recent discovery of the Higgs boson. And then we look at the macrostructure of the universe, and we think of the recent space-based telescope that was sent out into space, the James Webb telescope, which is going to look and is looking at the universe through the eyes of infrared, and they're going to see even deeper into space, even deeper into our past. So this is a really fascinating topic, and I hope that you're going to enjoy it as much as what I have in preparing it for you. So let's move on to the outcomes for this first video lesson on astrophysics and cosmology. So in this video lesson, we are looking at stellar processes and evolution, and in particular we're going to look at stating that fusion is the main energy source of stars, and then describing the conditions that initiate fusion in a star. So we are going to look at only these two outcomes, but you're going to see they are fairly detailed. So let's start off with the definition of astrophysics. Well, astrophysics is a branch of astronomy that uses the laws of physics to describe the nature of celestial objects, namely planets, stars, galaxies. So it's a subset of astronomy in which we approach astronomy from a perspective of physics. Now, there's also astrochemistry, and this has become a bigger field in recent times, where we are looking for extraterrestrial life by looking for conditions on exoplanets which would lead to possible life. Defining cosmology. Cosmology is the study of the origin, evolution, and the eventual fate of the universe. So we've all heard of the Big Bang theory, and you may have heard of the Big Crunch theory, but we really do not know what the eventual fate of the universe will be. But we have a fairly rigorous theory of how the universe began, and like any theory, it has limitations. We also have a fairly rigorous and robust theory on the evolution of the universe over the past 13.7 billion years. Now, you can basically become a professional cosmologist and spend the rest of your professional scientific career in the field of cosmology, or you can do the same in astrophysics. So obviously these topics are huge, and so we're only going to focus on certain subsets of these two amazing fields of science. So we are going to focus on stellar processes and on the evolution of stars. And then we're going to look at dark matter and dark energy, which are very relevant topics in modern astrophysics and cosmology, and really are at the cutting edge of these fields. So starting off with stellar processes and evolution. And when we talk about evolution, now we're talking about stellar evolution. What is a star? Well, a star is a massive sphere of highly compacted gas that generates immense amounts of energy in the form of heat and light. Now, our closest star to us is the Sun. And if we look at this image, we can see that, and this is a photograph, and I would assume that it's in the X-ray section of the spectra, the electromagnetic spectrum. We see here that this is one giant ball of gas. We also see things like solar flares, which are basically the result of magnetic fields that are generated in the Sun, and plasma, which is to a large extent the state of matter in the Sun, following the magnetic field line. So when we look up at the Sun, and we obviously can't look at it for too long, we see a ball of gas that is 150 million kilometers away, and yet we still can barely look at it. So the Sun is undoubtedly a object that we all are and should be thankful for, and because without it we would not have energy that is required for life on Earth. So studying stars is a very, very important endeavor, and that is what we are presently doing in this video lesson, looking at how stars start and the processes in them. How do stars generate energy? Well, stars are born in large structures called nebulae, which consist of dust and gas. Now, here is a photograph, a very famous photograph, of the pillars of creation, which was taken by the Hubble telescope. It's a very famous image, and there are many images of the pillars of creation now, but when it was initially taken in high resolution by the Hubble telescope, mankind was in awe. And this is an active site of star formation, and you can see inside here that there are actual stars that are being formed. So there are many, many, many different shapes of nebulae in the universe. For example, another famous one is called the Crab Nebulae, or the Crab Nebula. Nebulae is the plural. So what happens in these nebulae is that turbulence in the hydrogen gas clouds of the nebulae lead to clusters of gas. So we get these gigantic clumps or clusters of gas. Now, when the clusters have enough mass, they collapse under their mutual gravitational attraction. So keep in mind that gravity is a purely attractive force, and the more matter there is, the stronger the gravitational attraction. So they get pulled together. And when this happens, this pulling together leads to the hydrogen heating up. This gas starts to heat up as it gets pulled closer and closer and closer together. And this results in what we call a protostar. So protos means first, proto means beginning. So this is the first stage of the star. This is the baby star. This is a baby star, if you want to call it that. Now the hot core attracts more gas, and this leads to an increase in mass and heat given off. Now the combination of heat and pressure causing the protons to stick together through this process leads to what we call nuclear fusion, which we have studied in the previous section. And this is when a star is formed, because here now is how the star actually generates heat and light energy, is through fusion. Now, depending upon the mass of the star, two different processes occur. So the first process is what's known as proton-proton cycle, or the PP cycle. And then the second process is known as the carbon-nitrogen-oxygen cycle, or the CNO cycle. And we are going to look at both of these in relative detail. So the proton-proton cycle consists of three main steps. So in the first step, you have two protons, or hydrogen nuclei, that collide to form a deuterium nucleus, which is an isotope of hydrogen with one proton and one neutron. Now, what has happened is you had a +1 and a +1 charge, and now you have a deuterium nucleus which has got one proton and one neutron, so it only has a +1 charge. So in order to conserve electric charge, a positron, which is the antiparticle of an electron, is produced, and then there's also a neutrino which is produced in the reaction. Now in the next step, another proton collides with a deuterium nucleus, and in so doing it produces a helium-3 nucleus, which has now got two protons, which makes it helium, and one neutron. And during this collision, a gamma ray photon is emitted. Then, in the next step, what we find happening is that two helium-3 nuclei collide to form a helium-4 nucleus, and two protons are given off. Now, these protons can then start the chain reaction again in step 1, as we have seen before. So the end result of this is that we have a helium-4 nucleus with two protons which can continue the chain reaction. Now, obviously, all of these protons are positive, and so they naturally repel each other through electrostatic repulsion. So in order for these protons to actually collide and to fuse, the conditions need to be of extremely high pressure and temperature in order for the collisions to overcome the electrostatic repulsion. And so this happens in the core of a protostar and in the core of a fully functioning star. So the PP cycle can be represented by the following nuclear equations. Step 1, hydrogen 1 plus hydrogen 1 leads to deuterium, which is hydrogen 2, plus a positive electron, which is a positron, and a neutrino. Step 2, we have a deuterium nucleus colliding and fusing with a proton, producing a helium-3 nucleus plus a gamma ray photon. In step 3, we have two helium-3 nuclei which collide to produce a helium-4 nucleus and two protons, which then go back to starting step 1, and so we have a chain reaction. So the PP cycle occurs in stars with the same mass as our Sun, but for more massive stars, the CNO cycle dominates. So the CNO cycle can be represented as follows. We can see it's a cycle, so it's got a cyclic structure. So we've got step 1, we've got step 2, we have step 3, we have step 4, we have step 5, and we have step 6, which then takes us back to step 1. So the legend is we've got protons, neutrons, positrons, we have neutrinos, and we have gamma rays. So eventually, most of the hydrogen in the star's core has been transformed into helium. This implies that the star can fuse helium, which leads to heavier elements, example carbon, nitrogen, and oxygen, and it does this until iron and nickel are formed. The CNO cycle uses the nuclei of carbon, nitrogen, and oxygen to produce helium nuclei. So let's start with step 1, which we find there on the diagram. So if we look at step 1, a carbon nucleus fuses with a proton or hydrogen 1 nucleus. So here we've got a carbon 12 nucleus. It fuses with a hydrogen nucleus to form a nitrogen 13 nucleus, and energy is released in the form of a gamma ray photon. I want to reiterate that for this collision to take place, it has to take place at an exceptionally high energy, because a proton is positive and a carbon 12 nucleus is very positive, and so naturally they would repel each other. Even under normal conditions, even if they collided, they would not fuse, they would bounce off of each other because of the repulsion. So this has to take place under extreme pressure and extreme temperatures. So in step 2, which we find here on the diagram, we have that an unstable nitrogen 13 nucleus decays into a positron and into a neutrino and produces a carbon 13 nucleus in the process. In step number 3, which appears here on the diagram, we find that the carbon 13 nucleus, which was produced in step number 2, now fuses with another hydrogen 1 nucleus, which is a proton, to produce a nitrogen 14 nucleus and a gamma ray. So it's a carbon 13 nucleus which fuses with a hydrogen nucleus, a proton, to produce a nitrogen 14 nucleus and a gamma ray photon. Step 4 is found here on the diagram, and in step 4 what we find is that a nitrogen 14 nucleus, which was formed in the previous step, now fuses with the proton and produces an oxygen 15 nucleus and a gamma ray. In step 5 of this process, which we find on the left-hand side of the cyclic diagram, we find that the unstable oxygen 15 nucleus that was produced decays now to a nitrogen 15 nucleus, and a positron and a neutrino are produced in the process. Now in step 6, which is the final step in this cyclic process, and we find that here, we find now what happens is that the nitrogen 15 nucleus that was produced in the previous step now fuses with the proton, producing a helium 4 nucleus, which we also know is an alpha particle, as well as a carbon 12 nucleus. And this takes us back to the start of the CNO cycle. So here we can see the nitrogen 15 fuses with the hydrogen, producing a helium nucleus and a carbon 12 nucleus, which can then go on to fuse with another hydrogen nucleus, a proton, to start the process all over again. So it is very clear that this is a cyclic process that can continue on and on and on and on and on in the core of stars. So the result of the CNO cycle is identical to the PP cycle, because 4 hydrogen atoms fuse to form 1 helium atom. The nitrogen and the oxygen always react to form carbon again. The PP chain reaction starts at about 14 million Kelvin, which implies that it is the dominant mechanism in smaller stars, example like the Sun, which is, as we'll see later on in this topic, is a yellow dwarf star. The CNO cycle becomes the dominant source of energy above 17 million Kelvin. This implies it occurs in the cores of stars with at least 1.3 solar masses. So obviously in heavier stars, which have got a higher gravitational attraction, which results in higher pressure and higher temperatures in their cores. So to summarize, in this first video lesson in this topic, we have defined what a star is. We have looked at how stars produce energy through two fusion processes, the one being the proton-proton cycle, which occurs and which is the dominant process in cooler stars that are around about 14 million Kelvin. And then the second process is the CNO cycle, the carbon, nitrogen, oxygen cycle, which is the dominant source of energy above 17 million Kelvin. So these are the two fusion processes which ultimately produce helium and energy. And this energy is the energy that we perceive when we look at stars in the form of light, which travels across the universe, but obviously in close proximity to the star, huge amounts of heat energy are also radiated out. And for instance, with the Earth, we have life on Earth because we are just at the right distance from the sun to get enough of its light and heat energy in order for life processes to be able to function in a sustainable way. Now, in the next video lesson, we will look at what makes a star stable, and then looking at techniques on how to determine the temperature of a star by looking at the color of light that it emits.